Hey everyone, welcome back. This is going to be another math skills video. We're going to be looking at scientific notation, which I think is something that's probably overlooked a little bit in people's preparation for section 3. Basically, what we're going to look at today is why you should always work in scientific notation, especially if you're not very comfortable with doing kind of complex calculations with decimals and things. That being said, GAMSAT doesn't really need you to be able to do like 0.21 times 0.375 or something to a great degree of accuracy, but you can stay pretty accurate if you work in scientific notation, and you can usually work with much simpler numbers as well. So what we're going to do first is I'm going to break it down into a few kind of staggered lessons almost that slowly build up in difficulty. We're going to start with step 1, which is just converting into scientific notation. For people who aren't familiar, feel free to skip this bit if you are. So even if we had something really simple like 0.2, yes, we could think of that as 1/5 as well, and if you want to do that, you can. But we want to think of everything in this form where we have a number out the front times by 10 to the power of some exponent here, right? Power, index, whatever you want to call it. And the idea is by doing this and writing it in scientific notation, you can then apply index laws to all the bits that have the times 10 to the power of, because they'll have the same base, which makes that way easier. And then the number out the front, whether it's like 2 or something like that, then you can group all of those together as well and then do nice simple multiplications there and avoid having to deal with the decimals or the large or small numbers altogether. So if we had 2, for example, we want to basically move the decimal point until the number becomes a whole number. So here we can move that across one spot, so it becomes a 2. And then we put times 10 to the power of, and because we move to the right or it's a small number, we put -1 because it was one jump to the right, negative because it's a small number. If it were 2 jumps, like this one here, we have to go 1, 2, it now becomes a 7, but because we've made 2 jumps to the right, the power is -2, like this. And these are now in scientific notation, and it's much, much easier to work with than when you're going through the maths. Again, this one here, this would be 1 by 10 to the -3. And if we have large numbers, then it means the decimal point is sitting at the end, and we have to move it to the right. Now, technically, we could move it 2 spots until it becomes 3.18 by 10 to the 2, because it was 2 jumps. But you could also call it 31.8 and just make 1 jump times 10 to the 1. You could also leave it as 318 if you want. What you can also do is things like, you could just call this here, you could just say, well, that's basically 3 times 10 to the 2, like that. And that even cleans it up even further. We are using mostly estimates in the test, right? So this is our converting method. Step number 2 is going to be looking at how we actually calculate with grouping and actually showing why this skill is so useful. So say we had something like this. It comes up a lot in physics and chemistry questions where you kind of get hit with these weird fractions. I did a video last week about how to make estimates and that kind of thing. This is a different kind of way of looking at things. So if we put all of these into scientific notation, I'm going to go to whole numbers. So with the first one, I have to convert like this, and I'm going to write it as 18 times 10 to the -3 times this one here, 3 jumps as well. So that will be 2 times 10 to the -3, and then all divided by, and this one is 3 jumps as well actually, 36 times 10 to the -3. And then what I can do is, you can see, I'll color code this, is all of the numbers out the front can be grouped together, and all of the 10s can be grouped together. So if I do the numbers out the front first, I get 18 times 2, which is 36, over 36. And that obviously cancels out to 1, I'll come back to that. If I do in purple all the 10s, right, then what I can do is I can apply index laws here. So this is 10 to the -3 plus -3 over 10 to the -3, which then the numbers out the front give me a 1, which is nice and easy, times 10 to the power of. Up here I get -6, and then when you apply another index law, when you're dividing, it would be -6 over 10 to the -3. We subtract the powers there. And because we're subtracting a negative, double negative becomes a plus, and we end up with -6 plus 3, which is 10 to the -3, like that. And there's our answer. And then if we wanted to, we can convert that back and we can get it to 0.001. But realistically, the answer will probably be in that form. So if we practice that again one more time, just to prove that it works, we've got here 4,000 large numbers now. We've got to move it 1, 2, 3. We could call that 4 times 10 to the +3 this time. And then this one here, we can jump 1, 2, 3, 4, 5. We're going to go all the way across to 14. That's 10 to the -5. Again, 4 times 14, it's a little bit messier, but we can still reasonably do that and get 56. And then here we can get 10 to the positive 3, 10 to the 3 plus a negative 5, which is 56 times 10 to the negative 2. And if I wanted to, I could move and apply that and move the decimal point back to the right, back to the left 2 spots, and it would give me 0.56. So I've avoided actually dealing with the large and small numbers, and yet I've still been completely accurate without a calculator. That is the value of this, right? Now I've put in this other example with where we're adding, right? So we've only done ones with timesing and dividing. If you're adding, it's also really useful because you can think of them as like algebraic, like terms, so long as the power of the 10 is the same. So right now, these two numbers are not the same. This one's got a 10 to the negative 3, this one's got 10 to the negative 2. But if I express them both with a 10 to the negative 3 or both with a 10 to the negative 2, then I can add the numbers out front. So let's switch them both to 10 to the negative 3. This one's already good to go. This one here, if I was to make it 10 to the negative 3, I would have to move it 1 spot more to the right, which would then bring it up to 60. Any empty spots that I'm jumping over get filled in with zeros. So this would be like 60 times 10 to the negative 3. So I've got 5.4 times 10 to the negative 3 plus 60 times 10 to the negative 3. And so really in the full maths, it's not a maths test, right? But the reason why we're doing this is because we could factorize out a common factor of 10 to the negative 3 like this. And then what are we left with? We're left with 5.4 plus 60. I prefer to just think of it as 5.4 lots of 10 to the negative 3 plus another 60 lots of 10 to the negative 3. It's a little bit quicker, and you get 65.4 by 10 to the negative 3. Again, if we want to convert that back to a decimal, we can go 3 spots to the left, 1, 2, 3. We've got an arch there that's empty, so that will be 0. So we get 0.065. And there's our answer. Again, I've done that fully without actually having to know what 4,000 times 0.000014, if I've got that right. You can do it in scientific notation. So even if the number is simple, like 0.3, just write it as 3 by 10 to the negative 1. It'll make life easier if it's getting combined with other complex numbers. Cool. So what I thought I'd do as well is go through an actual ACER question. Again, I can't actually have it on the screen, but I've put the reference there. It's the purple book, which is test 2. I know they've changed the cover page a little bit and changed up the design. The questions are all the same. And it'll probably still be question 8 as well from the purple book. So with question 8, we've got time along the bottom, and we're told that it's measured in minutes. And then we've got increments 20, 40, 60, 80, 100, and we've also got over here the concentration of X measured in moles per liter, and we're being asked what's the rate of concentration change at the time. Let me fix this. So it's the rate of consumption of X at time t equals 30 minutes, right? And it's going to be measured in moles per liter per second. So really that's just the gradient at that time, but obviously it's curved, so the gradient is changing. And this seems like, how could scientific notation at all get involved in this? But we'll apply a little bit more maths. We find where 30 is, and we scan up, and it's a little bit wonky because my lines aren't lining up perfectly, but shows how good my artistic skills are. It means we're somewhere between these two data points. Now what we can do is we can make an assumption that if we connect these two data points, it won't be a perfect estimate, but it'll probably be the closest estimate we've got. If we tried to connect 2 points that are further away, you can see it's not really representing the slope of the curve at that point at all, right? Anyone who's done calculus or anything might have a little bit more background with that, but anyone who hasn't, don't worry, you don't need to know calculus to do this test. So we take these 2 points, and I'll read these off, the y values that we're given there for each of those 2 points. So around about 0.075 for this one, and around about 0.055. So we're actually just using the basics of linear relationships here. So gradient is rise over run, however you've learnt it at school. It's the difference in the y values divided by the difference in the x values. So if we think of these as coordinates, this would be 20 and 0.075, and this here would be 40 and 0.055. And so from there, if we're trying to do that in the maths, it's actually not that bad. Like we could just do 0.055 take away 0.075. You may be able to do that in your head. And then here we've got 40 take away 20, and we're going to estimate this rate. And we're approximating it as linear, and it'll be close enough because again, it's a multi-choice test. So here we can do this and get 0.02 over 20, but you might also want to write these as 5.5 times 10 to the negative 2 take away 7.5 times 10 to the negative 2. And because they've both got 10 to the negative 2, you can do 5.5 take away 7.5 is negative 2 times 10 to the negative 2, like that. And that's the same thing as 0.02. So that's where we're going to jump in now. If we write that as 2 by 10 to the negative 2, and we write the 20 as 2 times 10, then we can see now, 10 to the power of 1, we can see that the 2's cancel, and we end up with 10 to the negative 2 take away 1, which is 10 to the negative 3, which is the same as 1 times 10 to the negative 3, or 0.001, like that. And then from there, we look at the answers and nothing actually matches. 1 by 10 to the negative 3 is not actually shown. And so instead what you can do is you can go, all right, well, what are the answers in? If you scan through them, all the answers are either 10 to the negative 3 or 10 to the negative 4. The 10 to the negative 3 answer doesn't actually have 1, it has 2.2, so that can't be it. If we convert this into a 10 to the negative 4, then we have to move the decimal point 1 spot to the right, and we can say that's 10 by 10 to the negative 4. It's equivalent, these are the same thing. And now we can look at it and we go, which one's closest to 10? And we can see that option C is closest to 10 at 9.5 by 10 to the negative 4. So this is why having a good understanding of how scientific notation works can actually be helpful in the test. It's not going to be a straight up maths question. It's going to be checking if you know how to work with those numbers, right? The gradient bit is not the focus of ACER, I don't think, here. The focus is to see if people are going to trust their maths when they get to the point here and their answers don't match. And if they still understand that you can express it in other kind of, in other ways that are equivalent. Cool. All right, and if we do the same thing, there's a bit more of a complicated one with buoyancy in the purple test as well. It's questions 29 to 32. We're given this idea that we've got this wooden log with an unknown mass, and it's floating in a body of water which is shown. And we're told the dimensions of the wooden log, I'll zoom this in case it's unclear, is 0.2 meters long, 0.1 meters tall, and its other dimension in terms of its depth is given as 2 meters in the question, but it's not shown in the diagram. And this diagram is given in the question as well, like that. We're also given in the STEM that the density of water is 1,000 kilograms per cubic meter as well, but we're not given the density of the log, and then we get a bunch of different questions. And so we're going to use scientific notation throughout to make the calculations way, way easier. So question 29 will ask us about the vertical distance between the center of mass and the center of buoyancy. Now this one we don't really need to use scientific notation, but let's just prove the point. The idea is that the center of buoyancy is the midpoint that is submerged, and the center of mass is the midpoint of the object. And so we assume that is halfway through the height. So half of 0.03 is 0.015, which would be that little distance, all the way to the center of gravity, which would be to the center here, would be half of 0.1, which is 0.05. And so therefore the difference in them is 0.05, take away 0.015, which is 0.035, if I can write properly. All right, there we go. That one's not too bad. Question 30 then says, what is the density of the log? So we have to work that out. Now, density is just mass divided by volume. So we can start off, we can work out what the mass of the log is, because the rule, the Archimedes principle, is that the weight of the water that is displaced is equal to the weight of the object displacing it. So we're going to use mass instead. We're going to say that the mass of the log should be equal to the mass of the water that is displaced. Obviously, we don't have a measure of the exact volume of water here, but we can work out this little rectangular box of water that would be getting displaced. So the mass of the log we don't know, but on this side we can work this out. This would be density times volume. And density was given as 1,000, and the volume we can work out, it's length by width by height, but only of the bit that is submerged. So the length is 0.2, the height is 0.03, and the depth of it was 2 meters, like this. Now again, you might be comfortable doing that calculation, but just to prove the point, Let's just do it in scientific. This would be 2 by 10 to the negative 1. This would be 3 by 10 to the negative 2, and that would just be 2. We can group all, and we can even do this one actually. We can write the 1000 as just 10 to the 3. We can group all the non-10s, 2 times 3 times 2, which gives us 12. And then we can group all the 10s, and we can just apply the index law really quickly. 3, take away 1 is 2, take away 2 is 0. So that's 12 by 1, 12 kilos. So we've got the mass of the log, but it asked us for the density. And so then we go, okay, so the density of the log is just the mass of the log divided by the volume of the log. So that is 12 divided by, and the volume of the log is length by width by height, which, let's do it in scientific notation, 2 by 10 to the negative 1 for its length. Its height is 0.1, which is 1 by 10 to the negative 1, and its depth is 2 meters. So again, we've got 12 over the non-10s, 2 by 1 by 2 is 4. Negative 1 take away 1 is negative 2. And then we got 4 over 12 is going to be 3. And then this here, we can flip this up to the other side and make it positive, applying more index laws. You could also think of it as 3 over 10 to the negative 2 and then do it. And there we go, which represents 300 kilograms per cubic meter. And there's our answer. The next one, I'll try to keep the picture kind of roughly in view. Let's go over here. So then 31 asks, well, it says that imagine if you put a 20 kilo mass on top of it this time, then, and it's directly over the center as well, so it's not going to tip it or unbalance it. What is the additional volume of the log that will now be submerged? So basically we can use the same concept again. ACE like to just continue to use that same logic of reasoning in different ways, right? So if you understand it well, you'll be fine for the STEM. So now the volume of displaced water should have a mass that is equal to the mass that was added. So therefore, 20 kilos should be equal to density of water times by volume displaced. And that is extra, we'll say, right? And so we create a formula for this. So 20 is equal to, I'm going to put the 1000, the density as 10 to the 3 already. And the volume displaced, it would just sink a little bit lower. So we don't know how much lower what that depth actually is, right? But we actually don't need it because it's asking us for what volume is displaced, right? What extra volume. And so we can just solve this here and go 20 over 10 to the 3 is that volume. We want to write that 20 as 2 by 10 to the 1 over 10 to the 3. So it's 2 over nothing, or 2 over 1 really, 2. Apply an index law between these two. 1 minus 3 is negative 2, like that. And they've given it in decimals, so we can convert back 1, 2, and we get 0.02. Oh, not kilograms, cubic meters. And there's our answer. So scientific notation just prevents you from kind of doubting your maths or just making a silly mistake. Even if you're really comfortable with your maths, I would avoid decimals where you can unless you're very comfortable with it, because little mistakes can happen and it's hard to trace them. And then finally, 32, probably the toughest one in there, also asks about, suppose an object is now placed on the log, but it's not 20 kilos anymore. We've got to work out what that mass is so that it fully submerges the log. And we use the exact same concept again. So you can see there were pairs of questions all the way through where they just did it in two different directions or just changed the variables a little bit, reapply, right? So in this one, we want the mass, which we don't know, we're going to work that out, should be equal to the density of the water, because that's going to get displaced, times by the volume displaced. And again, we're going to go with extra. So we already know that if it's fully submerged now, it means it's got to submerge the rest of that 0.07. So we can work out that volume. So this would be 10 to the 3 for its density. And its volume is going to be length, which is 0.2. The depth is 0.07. Now, the extra, because we're only doing the extra. And the other dimension was 2 as well. And again, if we do scientific notation on that, then we can call this 2 by 10 to the negative 1. This is 7 by 10 to the negative 2, and this is 2. So all the non-zero numbers, 2 times 7 times 2 gives us 28. And then we can apply index laws. 3, take away 1 is 2, take away 2 is 0. So again, we get 28 kilos, and we get our answer, just like that. If we were trying to do decimals, you'd get there in the end, but you're more likely to stumble, get the place value wrong, or something like that. this is why we want to do scientific notation. Cool. All right. Hopefully that was helpful. I try to keep these quick. It's a little bit longer because we've done a bunch of examples, but the actual process itself, go back to the first bit, and it's done in like 5 minutes. A very, very simple process that you can use across physics questions, chemistry questions, probably even some bio stuff with data and that kind of thing as well. Hopefully this is helpful. Like the video, subscribe if you haven't already, and I'll see you in the next one.